Along with VGG in 2014 was also another network called the Google Net. The Google Net obviously came from Google, focused on deeper networks but with an objective for efficiency, to reduce the parameter count, to reduce memory usage, and to reduce computation. So how did they go about achieving all of this? They had up to 22 layers in the network. Remember, VGG went up to 19. So the Google Net went to 22 layers. So the networks were getting deeper each year. They did not have any FC layers. How did that help? Recall that FC layers had the maximum number of parameters for both AlexNet and VGGNet. So by getting rid of FC layers, they reduced number of parameters. And what else did they introduce? They introduced a module known as the Inception Module, which we'll describe in detail over the next few slides. Please don't worry if you're not able to see this figure carefully. We'll describe it in more detail over the next few slides. It had a total of 5 million parameters, which was 12x less than AlexNet and significantly lesser than VGG. And it was the winner in the 2014 ImageNet Challenge ahead of VGG. VGG was a runner-up that year, and GoogleNet won the challenge with a 6.7% top 5 error. So as you can see, every year as the networks got deeper, the error started dropping significantly. Let's now talk about the Inception Module, which was a key innovation in their approach. The Inception Module looked somewhat like this, which was one of those units that keeps repeating in their architecture. So the previous layer's output was branched out into one layer which did a 1x1 convolution. In parallel, another couple of layers which did 1x1 and 3x3, another couple of layers which did 1x1 and 5x5, and another one which did max pooling and 1x1 convolution. So this was a local unit with parallel branches, and this local structure repeated many times in the neural network. As you can see, this Inception Module was stacked on top of each other to complete the architecture of the Google Net. So the naive Inception Module, so this was the final Inception Module that was in the architecture, but let's develop this slowly. So the naive Inception Module takes a previous layer. Instead of deciding a particular filter size, or VGG, which always relies only on 3x3, what the Google Net designers decided to do was they decided to do multiple such filter sizes in parallel and concatenate all of them. So you have a 1x1, a 3x3, a 5x5, even a 3x3 max pool, and they concatenated all of those. So the depth that you get in this layer after the concatenation would be the concatenation of all of those depths that you get as the output of each of these convolutions or max pooling. So they had multiple receptive field sizes, and they had a pooling operation which they concatenated depth-wise. But there is a problem here. Do you see the problem? The problem is this is computationally very expensive. Remember, we said for AlexNet that most of its computations are in its convolutional layer. While the parameters may not be high, remember, you have to take the filter and convolve on every part of the image, and that can be pretty expensive. And now when this Inception Module does this across a 1x1 convolution, a 3x3 convolution, a 5x5 convolution simultaneously, and then concatenates, things become even more computationally expensive. So what do? They introduced something called a 1x1 bottleneck layer to reduce the channel dimension before expensive convolution layers. Now let's look at what this means. So if you have a 56x56x64 volume, you can do a 1x1 convolution across the depth. So that filter would be 1 cross 1 cross 64. And if you do that, the entire 56 cross 56 cross 64 will collapse to 56 cross 56, because for each of those spatial locations, a 1 cross 1 cross 164 convolution will give you one scalar as an output, which means you'll be left with 1 pixel here, 1 pixel here, 1 pixel here, so on and so forth in the next layer, which would lead to a 56 cross 56. So remember, the filter size for this 1 cross 1 convolution would have been 1 cross 1 cross 64. That's the 1 cross 1 convolution, or the bottleneck convolution bottleneck layer we are talking about. But they had 32 such filters, which means 32 such 1 cross 1 cross 1 cross 1 cross 64 filters, which results in the output now becoming 56 cross 56 cross 56 cross 32, because of 32 such filters. So by doing the 1 cross 1 convolution, a 56 cross 56 cross 64 volume became a 56 cross 56 cross 32 volume. And you can imagine now that you could have, instead of 32 filters, you could have just chosen 3 filters, 4 filters, so on and so forth. So the depth could have been arbitrarily reduced by using this trick of doing 1 cross 1 convolution. And that's what the GoogleNet designers did in the Inception module. What does this help with? This preserves spatial dimensions and reduces depth, and it projects the depth to lower dimensions. So now the final Inception module, this was the naive Inception module we saw a couple of slides back. The final Inception module does the same convolutions, but now before doing those convolutions, applies 1 cross 1 convolution to reduce the depth, which means the number of convolutions or operations that you have to do will reduce because of that, and then does 3 cross 3 or 5 cross 5 convolution. This trick helps them become far more efficient in the number of computations. Also, you see here that there is a 1 cross 1 convolution after max pool instead of before max pool when compared to the other branches. The reason for that is max pool maintains depth. It maintains the depth at the same thing as what was given. So when you do max pooling, the max pooling is done in a 2 cross 2 neighborhood on each channel in the volume. So every channel, the number of channels remains the same. So they first do the max pooling and then do 1 cross 1 convolution to reduce the number of channels. And this Inception module brings down or increases the efficiency, brings down the computations, but increases the efficiency of the GoogleNet. So here is the complete architecture. So this is where the input comes in, and then you have a small stem network, which is a con pool and 2 times a con pool. So you repeat that again. Then comes all these Inception modules stacked one after the other. And at the end, you have classifier output with no fully connected layers. And in between, you see here that there are auxiliary classifier outputs. This is because it's possible that a gradient in the last layer may not reach earlier layers when you have many stacked layers across the neural network. So they also had intermediate classification outputs where they took the output of a particular layer, had a bunch of classification layers which had a loss, and that losses gradient was also backpropagated at these locations to improve the strength of the gradient to earlier layers for weight update. As you can see, the classification layer, both here and here, all of them had a structure of average pool, 1 cross 1 convolution, FC, FC, softmax. There were 22 layers in total. The parallel layers count as one layer. So these different layers that you see inside the Inception module, the branches, we just count it as one layer, given that it has a total of 22 layers, and the auxiliary output layers are not counted. Just from this end to the other end, together it's 22 layers in GoogleNet. So as you can see, each year since 2012, the networks got deeper and deeper and deeper. So the obvious question the researchers in the next year had was, how far can we take it? And they took it to about 150 layers, which we will see in a moment. So while asking this question, they try to understand how deep can you go with a CNN. And when they studied stacking deeper and deeper layers on a plain CNN, they found that a 20-layer CNN had a lower training error over the iterations of training than a 56-layer CNN. This was a little non-intuitive. And the same observation was also made on the test error in the same setting. So the 20-layer CNN had a lower test error over iterations when compared to a 56-layer CNN. Why would this be happening? A deeper model performs worse than a shallow model. This was a little counterintuitive to how research was progressing with CNNs at that time. One plausible explanation you could give for why this could be happening is the initial guess could be that the deep model is perhaps overfitting, and that's why the test error increases for a 56-layer neural network. You have more parameters and it perhaps is becoming more complex and hence is overfitting. But if that was true, the training error would have been stronger for a 56-layer network over a 20-layer network. Unfortunately, even there, the 20-layer network had a lower error, which means the 56-layer network was also underfitting. What could have been the reason for this to happen as depth of neural network increases? The answer for this lies in what is known as the vanishing gradient problem. The problem complementary to vanishing gradient is known as exploding gradient, but let's talk about each of them in one after the other. So if you took a simple feed-forward neural network, let's assume with sigmoid activations in each layer. So here is a very simplistic visual for that. You have x0, there is a weight 1 that comes in first layer, there is a sigmoid, then x1, w2 is a weight in the second layer, a sigmoid, and so on and so forth until the last layer. If you now took a loss L and wanted to find dou L with respect to dou x0, which is one of the initial layers inputs, you have dou L by dou x0 is equal to sigma prime, which is the gradient of the sigmoid function, into w3 transpose x2 into w3 into sigma prime w2 transpose x1 into w2 into sigma prime w1 transpose x0 into w1. This comes from applying chain rule. You work out the gradient in each step, considering a sigmoid activation function in each layer, you would get this. But the key point that I'd like to draw you towards here is that the gradient of the sigmoid is less than 1 by 4. Why is that the case? Because this is how the gradient of the sigmoid function looks. It starts at a 0, close to 0. It peaks at 0.25 and then falls down again. This comes from the shape of the sigmoid function. So the gradient is steep in this region. It increases, then starts falling and then flattens out again. So the gradient of such a sigmoid function turns out to be something like this, and the range is between 0 and 1, which means the gradient turns out as capping at 0.25, which means dou L by dou x0 has a bunch of values which are all less than 1/4. What do you expect will happen to dou L by dou x0? The product of very small values will quickly go to 0, and you have the problem of what is known as vanishing gradients. As you go deeper and deeper into a neural network, the gradients, especially if you have such squashing activation functions, the gradients are less than 1, and as they get multiplied over the several layers during backpropagation, the gradient becomes feeble and feeble as it proceeds towards the initial layers. In other words, the gradients never reach the initial layers, or the initial layers may get stuck with the random initialization that we came up with and may never go further. So you could argue that instead of randomly initializing the neural network with some random weights and then not updating them at all convincingly, why have those layers in the first place? Let me not take such a deep network. That could be one way of arguing against to solve the vanishing gradients problem, but we'll talk about a different approach in a slide from now. The complementary problem, known as the exploding gradients, can happen when maybe there is another activation function such as ReLU, where the gradient could be 1 or greater than 1, or depends on what the activations are, or as I said, any other function where these terms end up becoming greater than 1. The product of those values, as you go deeper through many layers, can explode to a high value, and that also can cause problems. However, exploding gradients is often easily handled by a trick known as gradient clipping. This is very popularly used in practice. People just say that when gradient goes beyond 10, for instance, you assume the gradient to be 10. So anything greater than 10 will just be 10. You just clip it at that value, and that will ensure that the gradient does not explode. Coming back to the vanishing gradients problem, this problem was addressed in a CNN architecture in 2015 called ResNets, or residual nets. They wanted to ensure that a deep model should at least perform as well as a shallow model. How is this possible? The idea they came up with was to introduce what are known as residual blocks, which are connected to each other through identity connections or identity matrix. What does that mean? In the original CNN, you have an X. It goes through a few layers such as conv layer, then a ReLU, then a conv layer, and it gets transformed over those layers and becomes a certain h of X. This could be one portion of a neural network, for instance. But in a residual block, what these designers came up with was to say that X goes through a conv layer, a ReLU, a conv, just as in the vanilla CNN, but they also have a side channel to take the input X as it is and add it up here 2 layers later. Which means what was originally the function h of X now becomes f of X, which is the new transformation that happens through these layers, plus an X that comes directly here and gets added at this layer after the conv. Each such block where the identity connections come back and add the original input is known as a residual block. Why is it a residual block? Because originally these layers captured a function h of X, but now these layers capture the residual h of X minus X. Remember, now we are saying here that this together here must be equal to h of X, or rather f of X will be h of X minus X, which is now the residual rather than h of X itself. So the way the residual network was designed is to have a stack of many residual blocks. Each residual block had 2 3x3 conv layers, as you can see, 2 3x3 conv layers, and then the X that came out of this, or whatever representation came out from this particular joint here, was directly passed on again to the output of those 2 conv layers, and this was repeated again and again over the blocks in the neural network. Periodically, the number of filters were doubled. So you can see here that 64, which was the number of filters in the initial residual blocks, became 128 after a set of residual blocks, which after a few more residual blocks became 512 and so on and so forth. And it was also downsampled spatially using stride 2, that is divided by 2 in each dimension, to bring the size of the feature maps lower as you went deeper. Remember, that helps you control the number of neurons in later layers by downsampling the feature maps. They also used a technique called global average pooling. Global average pooling is like max pooling, average pooling, but global average pooling is the entire average of a feature map. So if you have a feature map, you take the average of all the pixels in that feature map and it gives you one scalar. So if you had k channels in a particular layer, by doing global average pooling, you will get k scalars. One scalar per channel, which will be the global average of that channel. You can imagine that as giving a feature map, taking the average intensity of that feature map. That is global average pooling. And then for each channel, you would get one global average pooled value. So if you had k feature maps, you would get a k-dimensional vector as the output of global average pooling. And they had a single linear layer at the end. You can see that there are no fully connected layers here, but for the FC1000, FC1000 is done because ImageNet has 1000 classes. So FC1000 is required to give 1000 outputs in that last layer. And finally a softmax to convert those logits into probabilities. They had total depths of 34, 50, 101 and 152 layers for ImageNet. So it's called ResNet 34, ResNet 50, ResNet 101, ResNet 152, so on and so forth. For very deep networks, which went beyond 50 layers in a ResNet, they also used a bottleneck layer. You can see the 1x1 convolutions to improve the efficiency, similar to GoogleNet. Remember, the 1x1 convolutions help you reduce the depth from a certain depth to a smaller depth, and then you perform your operations in that smaller depth, and you can again now do 1x1 convolution to go back to an initial depth if you like, which is something that they did do to keep the depth in the same range but reduce the computations by a couple of 1x1 or bottleneck layers, couple of 1x1 convolutions or bottleneck layers periodically. So this is the example. They had a 28x28x256 input. They bottlenecked it to 28x28x64 by doing 1x1 convolution, then do the 3x3 convolution only on those 64 feature maps, and then once again did 1x1 convolution and took it back to 28x28x256. This actually keeps the dimension the same as the input, but these 1x1 convolutions make the number of computations far lesser and hence the training more efficient. With this ResNet, they were able to train very deep networks. As we mentioned, they went up to 152 layers to train on ImageNet, and they now found that deeper networks actually perform better than shallow networks. Why so? Why does this identity map or this residual block help train deeper networks? When we backpropagate, the gradient that comes to a particular point in the residual network, while there is a path of the gradient through these layers which may result in an attenuation of the gradient, there is another side path for the gradient to go as it is to a previous layer without any diminishing in its value. And these identity connections that connect residual blocks serve like highways for the gradient to just flow through. They are like short circuits. The gradient just flows through them, while there is a part of the gradient that still keeps coming through the layers. And that allows even the earlier layers to get a strong gradient signal. And now deeper networks perform better than shallow networks. And it won the first place in all ImageNet competitions and also a competition called COCO that was introduced in 2015. So in fact, they won the the first place in all the major challenges in 2015. ImageNet classification, ImageNet detection, where they were 16% better than the second best. ImageNet localization, where they were 27% better than the second best. COCO detection, where they were 11% better than the second best. COCO segmentation, where they were 12% better than the second best. We will discuss detection, localization, segmentation, and the COCO dataset a bit later, but just to let you know that this model swept through all challenges in 2015 and has since then been an important architecture that people use for various applications in computer vision. So the homework for this lecture is to go through this illustration of 10 CNN architectures, which is very well done, which would perhaps help you understand these architectures better. If you're further interested, you can go through these respective papers, which are for ImageNet, residual connections, ResNets, VGG, so on, which could probably help you understand some of the decisions which were made in the design of these architectures. The exercise for this lecture is going to be show that minimizing negative log likelihood in a neural network with a softmax activation function in the last layer is equivalent to minimizing cross entropy loss function. We are not going to work this out in the next lecture. Please read this chapter 3 of Nielsen's online book if you would like to understand this further. With that, here are your references.